Hello, hi, welcome back to this class. This class is about Transformer. Um, Mainly we talk about encoder. In previous classes, we had 6 parts of Transformer, and in every single video, I talk about one single sub-block of Transformer encoder. So now in this class, I'll go through the whole block for the Transformer encoder. So this class kind of usually more longer than the classes that I provided earlier about every single part of the Transformer. So let's dive in because it's a longer class and because I explained each subclass for sub-process of encoder previously, so I might go a bit faster than it is. Now, here we talk about the transformer. A good definition of transformer is that it's a neural network architecture which was coined or coined in the paper, actually. Attention is all you need in 2070. That's done by Vasvani and his colleagues. So transformer, it has 2 parts, encoder and decoder. What's encoder? Encoder is about reading or reader, okay? It's a system or a component that reads and understands the input. And decoder is a writer, so writes output. So actually produces output, okay? So the exact architecture depends on the task. Some models use only encoder, some others they use decoder, and there are other models that they can use both. Now, here is the encoder and decoder. If I just take you through, this is encoder and this is decoder. Now, here in this class, we talk about every single process of encoder. That's what's the aim of it. Now, the encoder processes the input sequence and creates a rich contextual representation of every input token. For example, if we have a sentence and that sentence is the cat sat on the mat. So the encoder converts every word into an embedding and then allows each word to look at every other word using self-attention. And we come to self-attention. It's a technique that made AI models faster and more smart and generative. Now, for example, sat attends cat and mat attends on, and the attends and the attends the nearby words. So as a result, each output embedding contains information about the entire sentence. Now, in coder structure, we could have input embedding and then positional encoding, multi-head self-attention, add residual layer normalization, feed forward neural network, and add layer normalization, then the output. So usually there are 6 to 24 encoder layers when we talk about large language models. So it's not only one encoder layer, you might have several encoder layers for complex problem. But the example that we take in this class, it is simple. The main purpose of this example is to learn the physicality, functionality, and mechanism of how encoder can be implemented and work. So that's the self-attention. Self-attention has 3 parameters: query, signified by Q, K, signified key, signified by K, and value signified by value V. So the attention is a softmax. Okay, softmax is an activation function. You would have matrix Q and matrix K transfer over dk square root, which comes from the compact of D model, and D model is the dimension of the features that you have, multiplied by the value. And um, this lets every word determine which other words are most relevant. So they'll give you the word itself, where it is, and the relation of that word to other to other words as well. So here we have an example for decoder. We talk about decoder. Decoder is a writer. So we have the output sequence, one token at a time for the prediction. So we have how are you? And that's not encoder, that's decoder. Just explain it. How are you? And then the output in French, comment allez-vous? The decoder predicts commenter, and then after that comment allez, and then allez-vous, the next word vous will be predicted. Now, decoder structure, each decoder layer contains previous output tokens, uh, positional encoding, masked multi-head self-attention, add and layer norm, encoder decoder attention, add and layer norm again, feed forward network, and add layer norm, linear softmax, and next word. So that is what we have. And there's also mask self-attention. Well, during generation, the decoder should not see future words. For example, if I have a sentence and target sentence, it's I love AI. I love AI. So when predicting love, I should not see AI, the word AI. I should only see I when I'm going to predict love. So only the word uh, before itself can be seen. Now, real world analogy, imagine translating a sentence, encoder reads the entire paragraph, understands its meaning, creates a kind of notes summarizing every sentence and how they relate to each other. Decoder, it's a writer, uh, uses those notes, writes the translation one word at a time, refers back to the notes whenever needed. Now, basic differentiation between encoder and decoder. We've got model, encoder, decoder, and typical tasks that they can perform. For example, we have a BERT model, mainly consists of encoder, doesn't have decoder, and it can be used for text classification, sentiment analysis, answering um, uh, sentiment analysis, text classification, question answering, things like that. Now, GPT does have decoder, so it's mainly using for text generation, chatbots. For example, you have a soft bot or chatbot that you can question and get the answers. Code generation, story writing. T5, it has both encoder and decoder. It can be used for translation, summarization, PDF documents, question answering, text to text task. And there's also BART can use both summarization, text generation, document rewriting. So BERT can also use decoder, can only use decoder. GPT, BERT can only use encoder, and GPT can only use decoder. So if we come to the system, let's explain this part in this class. Starting this class, we explain input embedding and positional embedding. And I said that I need to go faster because these are explained separately in each video. So this part you can find in part 2 video. So we will have a sentence, I like Rojava, that's in Kurdish, and we want to translate it into Arabic. So we need to represent input, step one, encoder input, and we have tokenization, token integer index, and embedding plus positional encoding. Now, Tokenization means that each word, it's a token. For example, we have token 1, I, token 2, like, token 3, Rojava. Now we have N tree tokens. Three tokens. And now vocabulary mapping means that every token can lead to an index. So I index 5, like index 17, Rojava index 2, 103, and pad is index 0. Now, so the input sequence becomes in an array, one dimension, 5, 17, 203. So that is the integer input vector. For that, we need embedding layer, which is embedding layer. Each token index is converted to a dense vector, assuming embed dimension. This is for learning. I like Rojava, so I took only D model 4. Usually, you might have a bigger D model dimension, so you might have more than 4 features. You might have a lot of features, okay? Now, vocabulary size is 3 and embedding dimension, I assume it's 4. So now we have an array 3 by 4, okay? And here is embedding point 2, point 1. That's the habit for I, and this is for like, and this is for Rojava. 3 words we have it, or 3 tokens in our sentence example. So here is I, and this one is like, and the third one is Rojava. Now 3 by 4. So each row represents a word in our sentence. Now positional encoding, this is since we do not have recurrences, since this one has been tackled by the transformer in earlier models, in traditional models, for example, long short-term memory, LSTM, or recurrent neural network, we used to feed the system or model or machine learning word by word, or in time steps. So time one word, time two word, second word, and so on and so forth. But here we will feed the entire sentence, I like Rojava. So for this one, we need positional encoding, which we do not have recurrent. Okay, so positional embedding, this is the equation for it. This is for even, okay, if you have even index, and if you have odd index, so even index means 0, 2, 4, 5, 6, depends on the position that you have it. Position means the token sequence. So first token we have I like Rojava, that's 0. Second position is like, that is 1. And third position is 2, that is Rojava. And either it can be 0 or 1. Now D model is 4 and 2I over 4. That gives you this kind of the power of 10,000 to that formula, 2I D model. And I is the index, either it's 0 or 1. Now for position, starting from 0, we have a token I like Rojava. So that is I 0, and this I is for I equals 0. So 0, the first parameter is the token position, which is I. We gave it 0. And then the first, we do it for I 0, and we will feed I to here. 2 multiplied by I, it'll be 0. So sine 0 is 0. Now, second one, 2 multiplied by 0, that is 0, plus 1 is 1. So we see that here found 1. So that's for first token. For first position, we can, for first 2 positions. So for first, we said that 3 by 4. Now, the 4 you could have, now we found 0 and 1. And for I equals 1. Again, we feed 1 into here. 2 multiplied by 1, 2. And for E odd number, 2 multiplied by 1, 2 plus 1, 3. So we have 2 and 3. And again, the 0 is here, is the means the token. So now we found 0, 1, 0, 1. That's positional embedding for the first token, I. Now, likewise, we can do it for like, it's here. You can do the same thing, apply the same thing, you can get it. For Rojava, it is 2. Rojava means token 2, token 2, token 2, token 2. And 0, that's for the even. 0, 0 for the even, and you plug in 0 into this and plug 0 into this, so you would get sine and cosine for both of them. Now we found from the process that positional embedding for 2 is that result. Likewise, we can do it, I mean, detail about how I can implement these two equations. I have details in this slide, which is 0 means sine, 1 cosine, 2 sine, 3 cosine, and so on and so forth, because we have 4 dimensions. Now, so if you implement, as I did already, 2 multiplied by 0, 0, and 2 multiplied by 0 is 0, plus 1 is 1. 2 multiplied by 1 by 0 is, again, 2 multiplied by 1 is 2, as it is. 2 multiplied by I plus 1, it gives you 3. So it is kind of even and odd for each I equals 0 and I equals 1. Here more details about the denominator. If denominator is, for example, 2i, 2 multiplied by 0, 0 over 4, it gives you 0. So 10,000 to the power 0, it gives you 1. While 10,000 to the power of, if it's not 0, let's say you have I, 2 multiplied by I, 2 over 4. So I is 1. So 2 over 4 is half. So that's I is 1. So 2 multiplied by 1, 2 over 4. 2 over 4 and square root of 4, so that's 100. So anything denominator is 100. Now, that's what more about how to do calculation, easily done for you to understand it, and the slide is there. You can pause it and you can understand it. Very straightforward process. Now, this extra explanation of how we can get the results of positional embedding. Now, once I found positional embedding here, okay, I found it for I token, I found it for like token, and I found it for Rojava token. So 3 tokens. Each row is a token. Now, I added to earlier input that I have, which was the input vector, input index vector, which was this one. So x plus positional embedding. So this one I added to this one. So element wise, so 0 plus 0.2, 1.1 plus 0.1, 0 plus 0.7, 1 plus 0.3. So 1 plus 0.3 is 1.3, 0 plus 0.7, 0.7. So 1 plus 0.1, 1.1, and 0.2 plus 0 is 0.2. So that's the first row found. So element-wise addition. So element-wise addition, that means in matrix A and matrix B, you add element to other elements, or to the corresponding element in that matrix. So that's done now. We have this output after the positional embedding. Now, recap, that's the positional embedding that we found. This part is done. This is for I like Rojava. That's I, this, and like is this one second, and Rojava is the third. So each row represents one token. Now, lower dimension fast oscillation means that capture local order. Higher dimension slow oscillation means capturing long distant position. One changes quickly, the other slowly, because it's like that. So this creates unique positional fingerprints. Now, we've done with this part. Now let's do the second part, which is this one, multi-head. So we are here now. So let me explain multi-head. Recap what we have. So after the embedding and positional embedding, we have Z, this value, which we got it from here. Okay, that one. Okay, now we have it there. Now here we will try to get self-attention. Self-attention actually needs query K value, and this is the formula that was found in the paper in 2017. Attention is all you need. So softmax Q KT transfer K matrix over DK square root multiplied by V. This is the beautiful magic that was found that made the kind of large language models to be very advanced and to be very generative. So attention. Okay. Now, for that, we need to create or initialize three-weight matrix. One for Q, we call it WQ. One for K, we call it WK. One for value, we call it W value. So for query key values, three matrices can be designed. But these matrices can be lower dimensions. So we would have, we have our input that we got from embedding, positional embedding and input embedding. We got four features. Now we reduce it, we compact it to 2 dimensions. Okay, so for 2 dimensions, it means that we have 4 by 2, 4 rows and 2 columns. Here we have the initialization for each weight matrix, assuming, and then we will multiply Q by its weight matrix. So Q actually is 3 by 4, and weight matrix initialize 4 by 2. Now, any internal dimension when we multiplying two matrices, so the internal dimension will be eliminated and the size of the matrix will be 3 by 2. So outer dimension will be accepted. So here the first row of Q multiplied by the first column of the weight matrix. So the first column of the weight matrix 1, 0, 1, 0. And the first row of the Q is 0.2, 1.1, 0.7, 1.3. So we will get Q1 for the first row. So imagine what I did. This row multiply by this column. And the same row multiplied by this column. And then second row, like, this for I, the first one. Second row, like, again, multiplied by first column and multiplied by second column, and so on and so forth. So we get Q2, we get Q3, and that's the matrix for Q matrix, okay? Now we have to do the same thing for the K and V. We'll do the same thing for the K and B, but we multiply by different weights. So weight K is different from weight Q. So we will get the K as well. Similar. Row of K multiplied by column of weight matrix K. The same row will be multiplied by the second column, and the next row will be multiplied by the first column and second column, and so on and so forth. Likewise, we do it for the V, okay? And that's the V also done. Now, here we have, once we've done this one, we will have 3 by 2 key vector, value vector, okay? Because it was 3 by 4 and 4 by 2, then we have 3 by 2. Now, these are what we found the attentions, okay? Now, just check this formula. So we need to get softmax of Q function softmax key transfer multiplied by Q over dk square root. So in other words, this multiplied by transfer of this, and the transfer of this kt, it will be 2.4, 0.9, and 2.839. Then it will be 0.9, 1.55, 2.23. So that is K transfer. So converting this one to K transfer. Now that's what the K transfer that I did. Okay, exactly what I did there. So it is just changing the row to the column and column to the row. And now we are trying to multiply. We have Q 3 by 2, and we have KT transfer 2 by 3. So 2 will go with 2. We will have 3 by 3. Okay, so basic calculation, the first row multiplied by the first column and second column and third column, and the second row multiplied by first column, second column, third column, and so on and so forth. So this for the column 1, column 2, column 3 is done. So we found row 1. And for the row 2, we multiply by column 1, column 2, column 3, that is found. And for row 3 multiplied by column 1, column 2, column 3, that's found. Now we have this, that is the results of QKT. Okay, now we need to divide it by square root of dk. And what's dk? It is, dk means half of d model, okay? Because we are looking for 2 heads. So if we have 4 dimension divided by 2, so we have 2 heads, okay? Now, first, let me divide by dk square root. Dk square root means what? Means square root of 2. It is 1.414. Now, divide each one of them by, so that is the result that we get. So that's the scaled matrix. Now we need to do softmax for this one. The softmax for this one, it means that this to the exponential, exponential to this, and exponential to this, and exponential to this, sum them up, and this exponential to this divided by the sum of the exponentials that we have. Okay, that's softmax. So here, softmax, what it says, e to the power xi, and xi is 3.055. Okay, now we will find exponential for 3.05, 21.2. We will find exponential for 4.44. We find exponential for 4.66. Now we sum them up, and we receive 211.5. Now, and we take each one of them, so 21.5 over 211.5, and it is 0.1. Likewise, we will do the same for 84.6 divided by 211.5, and also 105.7 divided by 211.5. 11.5. So that is the result of the first row. We found the result of the first row. We'll do the same to find the result of the second row. And we'll do the softmax for the third row as well. And that is the A matrix we found. The A matrix is the softmax of Q multiplied by K transfer over square root of dk. Here there is some notes I would like to make sure that there are some points that we have to understand. Now, if you sum up the first row, you should get 1. And if you sum up the second row, you should get 1. And if you sum up this third row, you should get 1. That is the attention that we are talking about. So this is the I, and that's like, and this is Rojava. So the first row is I, second row is like, I like, and the third row is Rojava. And now you can see that when we say that 0.1 plus 0.4 plus 0.5, you should get 1. Likewise, other rows, summation of each row should give you 1. But now you see that I attends mostly to Rojava. You see 0.5 is kind of Rojava. And then here in the like 0.5, 0.5, 0.1. So like attends to itself because the second row is like and the second column is like, so attends to itself. Now here, Rojava attends mostly to like. It is 0.685, the highest. So here is the highest 0.5. That means I attends to Rojava mostly. And here like attends mostly to itself, 0.51. And in the third, you can see Rojava attends to like. So that is I wanted to explain each one of them. And you can see that Rojava attends strongly to like by 6.685, and this is like attends to itself by 0.51, and here Rojava, I attends Rojava by 50%. So that's the relationship that we are looking for. And if then next step, we have to multiply it by V. So we have the A, we multiply it by V vector, just normal vector, and that's the V vector is here. We found it earlier. So that's the V vector. So this vector multiplied by A vector, this vector, A. That's the A vector. And we will get the results of it. So A vector 3 by 3 and V vector 3 by 2, 3 internally, the two threes internally will be eliminated, and then we should have a vector 3 by 2. So 3 by 2. That is the vector that we are looking for. This is the output. That's the final attention that is that we have. That's the final attention. Now, so what is the benefit of multi-head attention? Well, the benefit is many, but I can say that, for example, I have a sentence, I like Rojava. So if you have one head, one person means one person you have, he is looking at the sentence. Maybe he's looking at it grammatically, syntax. Maybe you have another head, another person, he or she looks at it from semantic point of view, the meaning of so the more heads you have, the better contextual you have, the better understanding you have, the better relationship you have. Okay, so that is what we are having. So now next we do a mathematical concatenation of head 1 and head 2 multiplied by WO. That's another weight matrix output. But let's do the heads. Now in this example, I need two heads. The first head is already done. That's what we had, the first head. That's the result of the first head. So that's the first head. That is the result of the first head. That is the head is done. So the first head is done. Okay, now I'm trying to create another head. So another head, I need to create another weight matrix, initialize random weight matrix. Right now I have WQ initialize and WK to initialize, and two means the head two. One was earlier I did, that was um, for head one. Now, likewise, I do repeat Q2, the vector Q equals the Z that I have, the input before multi-head, before it goes to the head, and apply. For example, if I take you to the diagram, here we are here. If I take you to the diagram, so here you can see them here. That means the Z that can go here, okay, it goes to three branches. Okay, so that's head one, that's head two, that's head three, whatever you have heads you want to make. So now we have two heads, okay? Um, so that's multi-head. That's the idea of the multi-head. So we try to do the same exact uh, operation as we did. Uh, See, that is, I get the Q vector. So Z, which I took it earlier before getting into multi-head, that's the output from the embedding, positional embedding and input embedding. So the Q is found, Q2, and K2 is found, multiplied by its weight vector, and V is found. And I do softmax as I did earlier, multiplied by K2 transfer over square root multiplied by V2. Now that's the head 2. This is the head 2. So the head 1 looks at assuming that head 1 is like a person. One person looks at the sentence that I have, which is I like Rojava. And I have another head, means that another person I have. Imagine another person that you have. And again, that person looks at the sentence, but might think of sentence in different aspect and from the first one. So two different people, they look at the sentence. One might think, one might look at it from the grammar perspective. The other one might look at it from um, semantic perspective. So that's now we're trying to concatenate. What we do, we will bring the first head. Okay, that was the first head. Concatenate it 1.825, 3.515, and so on and so forth. And that is the second head. So the second head 1.1 and 2.85. And we put them, we concatenate them, we put them beside each other. So now that's the first head one. And this is the second head two. So we concatenate, we put them beside each other. Okay, 3 by 2, concatenate 3 by 2. It will be 3 by 4. 3 by 4. So row 1, row 2, row 3, uh, uh, column 1, column 2, column 3, column 4. So 3 by 4. Now, that's the concatenation. We multiply it by another weight matrix. We call it W and O. So, and that weight matrix is 4 by 4. It means 4 row and 4 columns. Now we have the heads 3 by 4, and then we have multiplying it by 4 by 4. So 4 will go with 4 eliminated internal. So you should have 3 by 4. We need to always preserve or keep the same size of the output so that it can go to the next layer in the encoder. So now we would have 3 by 4. 3 by 4. So why we did this one? Well, we have parallel semantic extraction. It means we might have multiple relationships are learned simultaneously and richer contextual representation. You know, each token is represented from multiple perspectives, as we say, multiple people, multiple heads, and multiple relational subspaces. Different heads specialize in different types of linguistic, some of them semantic, some of them uh, um, syntactic, or different semantics way. Okay. So now we did this one and we did this one. Now we are moving into this part. So we're here now, okay, which is add residual and norm. So this should be very simple because we have the attention as we have, okay? We have the attention as we have, the output from the attention, um, uh, which is here, plus original Z, original input before the attention. So, and you can see the diagram. You can see the diagram here. If I can take you to this diagram. Um, so here, so that is original input that comes here, put in red. That's the original input. Okay, so it is going to here. So we kept the original input and plus the output, which is here from multi-head. So now original input, and you see here as well, same thing. So we always keep original input. We keep just skipping. You see, that's residual. Skipping and coming to the yellow box. It was here, it comes from yellow box. So if I just make sure that have the diagram in a different way. So here, here is the Z that goes here straight away, skipping going into orange multi-head attention box. Now, so that Z plus the output from multi-head. So Z plus multi-head attention Z subject to that function. So that's what we are doing by, um, that's the process that we are doing, okay? So here we have the Z. If you go back, we have the Z 3 multiplied by 4. This is before the attention, okay? Original input to attention, okay? And then this is the output of the attention. So this plus this, and we do it by element-wise addition. So 0.2 plus 2.925, 1.1 plus 6.365, zero point 0.7 plus 4.675, and so on and so forth. That's how we work with it. And next, after we do this one, then we go to we're done with the residual. We are done with the residual. We are done with the residual. I just put the charger on onto my laptop. Now, why we did the addition element-wise? Well, we're trying to prevent vanishing gradients by doing residual, by doing adding residual, skipping and keeping the original. We want to keep original information in case that, for example, the multi-head didn't work well, still we have the original. And enables deep networks, allowing stacking many transformer layers reliably. So it allows to stack many transformer layers encoder. Now, the idea is transformer does not replace the original information. We always keep the original information, and it adds new layered information to refine the representation. That's the idea of residual, add residual layer. Now, here we are going to have adding, and we can say that this plus this and 0.1 plus 6, and that's we did element-wise. So that's row 1 done. Row 2, same is done element-wise. So we will have the final residual here. That's the final residual. So we're here, we've done the add, and now we need to do normalization. So we do the normalization next step. In the normalization, we have to find the mean, and the mean means what? Every features in each row in the matrix will be summed up with the next one. And then after that, we divided by the number of features in each row. And then we square root, we take each feature minus the mean, square root it, and then sum it up, and then get the standard deviation. Okay, so the first row, if I go to this, the information, that's the first row. We sum up this information, 3.125 plus 7.465 plus 5.375 plus 5.15. So all this will be summed up and divided by 4. And we do it for the second row again, divided by 4, and sum up the third row, divided by 4. And then we find mu in each in each um, um, row, okay, in each row. And then we take the value minus the mean, okay? We take this value minus the mean, 5.4, 3.125 minus 5.47. Likewise, 7.465 minus 5.74, you'll have 1995. Now, then we square each difference, okay? Now, here we square it, we square the difference, and we sum them up, and we divide it by 4. Then you get the deviation, variance. And square root of this one, square root of the variance, we will have standard deviations. Now here we found the square root of the variance, get the standard deviation. And now that standard deviation, we will divide each variation here that we have minus standard deviation, minus standard deviation. So the first row is found. Likewise, we do it for the second token. Simple as that. For the second token, we can do the same thing, and we normalize it. Likewise, we do it for the third token. Again, sum all this row up, divided by 4. Then each feature minus the mu, okay, get the difference, okay, that's the difference. Square root of this one, the difference. Square root of this one, difference. Square root of this one, square root of this one. Then sum them up, and we found we sum them up, so we found this one. Then divided by 4, we will find 0.5336. Now square root of this one, we will get 0.732. That is the, sorry, that is what? That is the standard deviation. Then that standard deviation, so each deviation, 0.92, divide by this one. 0.76, divide by this one. So minus 0.51, divide by 0.732. So therefore, we will get the normalize of the second layer. Now, the normalization is done in this case. That's our normalizer 3 by 4. Next, so we've done this one, we've done this one, we've done this one. Now we are going to two more processes to be done, which is feed forward and add a norm layer again. So now feed forward, here is the output from add and norm, which is we called X. Add and norm, we have add residual and norm normalization. That was the results earlier, remember? That was, we had it. Now we have to go make feed forward. In the feed forward, we will have a hidden one and hidden 2 layer. So we have 2 hidden layers. Okay, those they familiar with the neural network. So the first hidden layer, it is this part. Okay, this part only. That's the first hidden layer. So you have X, which is this one. That's X, multiplied by weight matrix 1, we initialize weight matrix, normal weight matrix, and plus bias. So once this one done, that is hidden 1. Hidden 2, it is simple. It's equal to hidden 1 that we found it from here, that one, multiplied by weight 2 plus b. That is the equation for it. So let's do it. So weight 1, 4 by 6, weight 2, 6 by 4, and I tell you why 4 by 6 and why 6 by 4 later on. So here is the weight matrix 1 for hidden 1 and bias for the hidden 1, weight matrix 2 for hidden 2, hidden layer 2, and bias for hidden layer 2. Now, we do the calculation, normal calculation, 3 by 4 multiplied by 4 by 6. That's why 4 by 6? That's 4 by 6. 4 row and 6 columns. So 4 will fall internal dimension. They will be eliminated. Then you have 3 by 6. That's the result for the first row. First row multiplied by first column, second column, third column, fourth column, fifth column, sixth column. So that's what we did. So we will get the hidden layer. That is the first row. Likewise, we will do what we call it, reactivated linear linear unit. So this is the function that, for example, function that takes the negative into 0 and max the positive. So that's nonlinear ReLU function. So that's our function. That was the result. So if you subject this one to ReLU, reactivated linear unit. So this one, every negative it will be 0. Every negative it will be 0. Every negative it will be 0, and the rest we will keep it as maximum. So that is the result of the first token I, and the result of the second token, and the result of the third token, and we found it. Now, once we found, then this is kind of the output of the hidden one multiplied by weight matrix 2, then we will get again weight matrix 2, we will get the feed forward weight matrix. So here for the token 1, that's for the token 2, that's for the token 3, and the final output is this one. Now we find the final output. Here, why do we need feed forward inside a transformer? Well, first, it has linear layer expanse representation. We had 4 features, and remember, we made it to 6. Remember, we had weight matrix 6 rows. Okay. Now, and then we had the input vector 4 features. The first layer increases to 6 features. So from 4 to 6, you'll be able to deal with more complex patterns because you had 6 features. Now you have you had 4 features. You move to 6 features. It means that you have to learn more complex patterns. Now, ReLU keeps positive values and sets negative values to 0. This allows network to learn more complex relationships instead of just simple linear patterns. Now, don't forget that H1 was nonlinear because of ReLU, and H2 is linear because if you go to the example here, so that's ReLU activation function, but this is all H multiplied by W plus B2. That's base H1 multiplied by W2 plus B2. So this is basic linear equation. So now you have a mixture of linear equation and nonlinear equation. A linear equation in the first hidden layer, nonlinear equation in the second hidden layer. That's very good. Okay, so second layer projects back 6 to 4. It brings it back to normal linear original size of the input and with the same dimensions. Now, what we tackled complex feature mixing. We had nonlinear transformation, and we had higher representation power. Now we expanded our space, information space, and we learned more complex features. And again, we're more flexible to go back to its original size of the matrix. Now we've done this one, we've done this one, we've done this one, we've done this one. Now we do last process of the encoder before gets into decoder to get cross attention. Now we have this X, we have this results we called here from feed forward, and we have this X from feed forward. We have feed forward X here, and we have X here before it goes to the feed forward. So X plus feed forward X. That's what we are doing. That's the final element-wise addition. That's X that we have before before going into feed-forward neural network, and that's the output of the feed-forward neural network. So this element plus this element, this element plus this element, this element plus this element, likewise this element plus this element, this element plus this element, and so on and so forth. So element-wise addition, basic, simple, straightforward. And then we do, again, layer normalization. We said that layer normalization, we will sum up after we added them. We will, for example, we add this to this, to this, and to this, divided by 4, add this to this, to this, to this, divide by 4, add this to this, to this, divide by 4, and we get mu. We get mu for each row, and then this one minus the mu, so each element minus mu, and square root, and again, once you square root, sum them up, and then divide by 4 and square root it. So that's basic. We did the normalization. Basically, we do it in relation to rows, not columns. So that is what we did with the normalization. I think it is all clear. Now, normalize. So the final output, it will be this one. So the final output, that is the final output that goes into encoder. Okay. And I think we need to, the encoder will take key and V. I think if I just rectify myself later on, key and V from encoder, and will be combined with the Q of the decoder. I think in the next step we can explain it. So, or send to decoder as K and V, as I said, for cross attention. So then the decoder will do the translation. Now, what happens, I can say, each token right now after the decoder, each token here, each token here, each token here, which is this one, each token, each word, that's word I, first one, that's word like, second row, and row Java. Each token contains contextual information, has controlled variables, and it's ready to be processed or passed to the next decoder, or sent to decoder as K and V for cross attention. So that's what we stop here. And just a small remark on what I done. So this is kind of the prediction token and the results might not be exactly the same training because this only for purpose of training. So we took simple weight matrix. We took simple uh, dimension model, D model. So we took only four. You might take 512, you might take 164. So this is just for learning. So the prediction might not be exactly same because it just we're trying to demonstrate the physicality, the mechanism, the functionality of encoder. That's the main purpose of this class. So stay tuned, and if you have anything, just let me know and drop email here or check for more information in there. I wish you all the best. Thank you.